I'm joined today by a very distinguished panel to talk about cleaning under low standoff equipped components. Let me make the introductions. On my left is Konrad, from CEO and President of Aqueous Technologies. Next to him is Mr. Umut Tosun, Applications Technology Manager from ZESTRON. And next to him is Emmanuele, Guéné, Technical Engineer from Inventec Performance Chemicals. And next to me here on my right is Tom Forsythe, Vice President of Kyzen Corporation. And next to Tom is John Neiderman. He is the Technical Engineer from Speedline Technologies. Welcome, gentlemen.
Glad to be here.
Now, cleaning challenges are evolving as further miniaturization has led to the use of ultra-fine pitch components like QFNs and microBGAs with standoff heights of typically less than 2 mils. So this makes cleaning residue under these components very difficult and leads to reliability issues. So perhaps I'll pose the first question to the equipment suppliers, which means you, Mike, and John. With lead-free solder processes at usually higher temperatures, which creates probably harder residues than normal, and also with plenty of flux compositions out there, how does the modern machines adjust to this? I would say perhaps a greater flow rate or increase in force and pressure. How would you say the modern cleaning machine would adjust to all these variations? Mike?
Well, it's a moving target over the years. You're correct in your statement that more flow, more pressure aids in cleaning. However, the most common way to get more impact pressure at the board is to increase the size of the water particle. When you increase the size of the water particle has a velocity, it has a mass to it, and it increases impact pressure. However, the larger the particle size, the more difficult that particle size is to get under a 2 mil, 1 mil standoff. So it's a combination of mechanically manipulating the size of the water particle so that you can get the water particles underneath the component, but while maintaining a sufficient amount of impact pressure. So it's a little bit of a balance, because what gives you one takes away from another. The issue generally isn't in the wash cycle because of the chemicals that are used in the clean business that lower surface tension, and you can get fairly easily. You can get wash solution under fine pitch components rather easily. The real challenge is taking that wash solution out from under it using higher surface tension chemical-free water in the rinse. And that's where all the mechanics come into play.
And John, how do you feel about this issue?
I agree with Mike. It's definitely with lead-free, with the higher temperatures, you see the flux starts to polymerize, or char, if you will, making it more difficult to remove. And so from vintage inline machines from back in the early 90s to today, we've substantially increased the amount of energy. And that's through thermal and mechanical, and then of course with the water-based chemistries to aid in the chemical energy. For instance, our older inline equipment at the substrate surface, we would see somewhere about 0.1 to 2 psi. With today's inlines, we're achieving upwards of 18 psi at the board surface to help break away that flux residue and remove it from the board.
So taking in what the equipment guys just said, let me ask the chemistry guys here. Is there a way that we could have an optimum chemistry equipment combination so as to clean these flux residues without harming the component, the board, as well as being environmentally friendly as well? Maybe Tom, you can
Sure, and you know, that starts with understanding the differences. You know, as John pointed out, you know, the inlines tend to have higher pressures. They also tend to have shorter exposure times. You know, the belts are moving and it's moving through the chemical zone rather quickly. Batch cleaners tend to have longer wash cycles, you know, more focused sort of cleaning. That sometimes can drive chemical choices from a formulation perspective. You may have a product that's a bit aggressive but works wonderful in an inline. With that long exposure, might not be the best choice on the batch side. You know, likewise, there's a lot of different soils out there in the market. There are no cleans. There's still lots of lead-ed fluxes floating around, as well as all the lead-frees and all the water-solubles. You know, that's one of the areas where there are big changes. With water-soluble folks are starting to experience this cleaning under LCCs and things. That's opening the door for new products from us, new products from ZESTRON. to address that, because those are folks, at least, and this is where there are two cleaning markets. I think you know, John and Mike would agree that people that were cleaning with water before were cleaning people. But I think the three of us would agree that those people really weren't cleaning because they weren't using cleaning materials. You know, it's a bit of a parochial perspective, but that's changing. They're starting to come into the market where the materials do help. And that's good. That's going to improve quality. That's going to improve the reliability of things. So that's a positive trend.
Umut, your views on this?
Absolutely. Normally, you know, we recommend our clients to run trials with different various cleaning agents and different equipment to get the most optimum combination from both the chemistry side as well as the equipment side. From the chemistry side, like Tom mentioned, we have to look at the reactivity of the cleaning agent, how fast it's capable of cleaning the flux residues, as well as the solvency, because some residues are more, responsive to the alkalinity of the cleaning agent. Some of them are more responsive to the solvency of the cleaning agent. Aside from that, John also mentioned that we have to look at the wash temperature, exposure time. In the case of the batch cleaners, the cycle time. In the inline cleaners, the conveyor belt speed. And after running trials, we surely get to find optimum settings for the customer's requirements.
Okay, so now we get to the lady. Emmanuele, you're the soldering expert. So could you tell us how much the reflow process comes into play regarding the residues and how that causes?
Okay, first when we have to look at the whole process, as you said, soldering and cleaning. And when we have to define an efficient cleaning process, we have to check the paste, the cleaning process, the cleaning agent, and all the parameters around which make the residue more or less easy to clean. We can consider that there are several types of solder paste. The water-soluble one, the no-clean, and the one which are designed to clean but with other, not only with water. If we look at the water-soluble solder paste, they are very aggressive, so you have a good results in terms of reflow, in terms of wettability. But these residues are very aggressive and they have to be washed with the water, or water with a little addition of detergent to help the cleaning. And if you look at the no-clean solder paste, they are designed for no-clean, but they also can be cleaned with either detergent process or solvent process. And all the parameters of the reflow will influence the residue hardness, the residue easiness to be cleaned. So the best is to stick to the reflow profile recommended by your solder paste manufacturer to avoid to have too much difficult residue to clean. Then if you really need to clean and you have a double reflow, after 2 reflows, it's even more difficult to clean. If you really need to have a good result, maybe you have to consider the option of cleaning after the first reflow and before the second reflow. So this is for as far as solder paste is concerned. And also something else, the residues are not equivalent depending on the solder paste manufacturer. Some are easier to clean with detergent, some are easier with solvent. So this is really to be the process itself, the whole process must be taken into account.
Right. So my next question is how clean is clean? Because if I'm a manufacturer, right, and I'm looking for precise and repeatable solutions, so how would I be able to achieve that? You know, Mike, maybe your views on that?
It's probably one of the most common questions that we get is how clean is clean, and the answer, unfortunately, is it depends. It depends on what the cost of failure is. The challenge behind that question is that IPC has a clear standard of what is considered clean and what is considered contaminated. And that standard came from the old 6536, which morphed into MIL 2000A, which morphed into the IPC J standards. And that number, when used with a ROSE tester, a solvent extract tester, that number is 10. 10 is fail, 9.9 is pass. Unfortunately, that specification was designed when Fantasy Island was the #1 show on television, and it was in the 70s. And components and assemblies are far different today than they were 30 years ago. And there's really been very little in terms of specification. No one really wants to plant a flag in the ground and come up with another number and another absolute go, no-go technique. So with our ROS testers, we tell our customers to 0.0 is a defendable number, 0.1 is defendable, somewhere between that and 10 is an issue. The most common way of determining how clean is with a ROS tester. There's thousands of them out there. They're an imperfect science and they're in a very rough approximation. So you can't just go by that number without doing further testing because the results are averaged over the entire surface area of the board, and of course contamination is not averaged in reality over the entire surface area of the board. So one needs to look at where the board goes, the environment that it lives in, the cost of failure. Is it an implantable device made by a medical manufacturer? Is it going into space? Is it going into a video game? What's the environment it's going to be in? Is it going to be in a humid environment? Combine ROS testing with perhaps ion chromatography with good visual inspection. Not enough people pull components off boards to look for contamination. And reliability testing, steam age testing, all these things can go in and come up with a number that's relevant for that specific application. And then use the common testers on the market to look for changes in process, not for a single evaluation on whether or not you should ship that board to your customer. It's one of many tools that are used to form an educated opinion over how clean that board is.
John, your point of view on that?
I agree with Mike. There's no one test or process that's going to tell you if your product's clean. First of all, you have to know, as Mike mentioned, what's your intention or the end use of the product, and as a manufacturer, understand what is reliable and what isn't, and what parts of your process are going to affect that reliability and performance. So what's important is upfront understanding that, and then going through the tools that are available, such as IC, SIR, ROS, and even visual, and then correlating all of that data together and basically coming up with an upper and lower control set point, so that then when you do move to your process, you can use a ROS tester to look for situations where you may start to go out of spec. There's a lot of time, money, and effort to do that up front. And so from an equipment standpoint, it's important to have that type of control, process control, so that not only are you looking at it from a ROS testing perspective, you're also watching the machine as far as the pressures, the speed, and the temperatures. That's also going to give you an indication of if you start to go out of your process.
And Tom, would you like to add?
Well, the key point that John brought up is that process validation up front. I mean, that's really where it happens, because ROS testers, as we move away from what the fluxes are no longer ionic, that's what a no clean definition sort of is. So ROS testers are looking for ionic residues. So if that's the contaminant we're trying to remove, that's not a great metric. That process validation up front, whether it's IC or FTIR or SIR, all the different tools that might be used, this is a process that works. These are the parameters that the process works in, whether it's reflow as well, because if people push up their reflow because they have a dense board and they're worried about some temperature in a few areas, well, all of a sudden that has a big effect on the soils and the process. If you do that after validation, well then you're not validated anymore. You need to do that up front, so then you can use these tools to make sure you're staying in bands. That's really key. The work up front, if you try to do it on the fly, it mostly doesn't work out.
All right. Umut?
I fully agree with Mike, Tom, and John. First thing is basically we start with the visual inspection to see if there's any visible residues on the boards or not. Partially cleaned residues normally tend to have a white powderish look on the board surface. And then the second test could be an accelerated failure test, which is a climatic chamber test, and expose the boards to varying temperatures and humidity to see if the boards will fail or not. And if the boards are to be failed, then we can continue with the ion chromatography testing and ionic contamination test to see, to detect the nature of the residues, whether they are ionic residues or non-ionic residues that's causing this failure. And if they are non-ionic, of course, ionic contamination will not be able to tell us, those residues. So we have to complement those tests with other test kits to identify if there are rosin-based residues or not on the board surface.
Emmanuele, to add on that?
I think you said all that has to be said.
Right.
I just would like to add that if you have an existing process, if you have this component very difficult to clean, you really need to check the quality of your bath and the quality of your cleaner, because you will have the window process of cleaning will be for sure reduced. So this is very important to have a good following of your bath.
Right.
Cleaning.
Okay. Well, thank you very much for sharing your considerable insight today, gentlemen. Thank you so much for your time.
Thank you.
Yeah, thank you.